when you see this node, which means if you don't compute numerically the value of the autocorrelation, you are better to give up. This is what it says, okay? Since I cannot say, I mean, he's recording, since I cannot be so unpolite to say that if you don't compute numerically the autocorrelation, you are better to skip the exercise. So this means compute it, okay? Now, number B. Evaluate the linear predictor of step 1 for yt in two cases, length 1 and length 2. Okay? So this one is a linear predictor of yn of length 1 and length 2. Okay? Now you understand why I choose this exercise. So I am making a linear prediction of y, okay, either length 1 or length 2. So it means I take this one, okay, and I am making a linear predictor. So in two options, the linear predictor is length 1 and the linear predictor is length 2. Okay? So what does it mean, length 1? It means that here I have a linear predictor length 1. So what is? That means that I need to estimate y hat n. This is the length 1, which is equal to a1 times y n minus 1. Okay? So that means I'm using one sample in the past to predict the sample in the future. And my unknown is this one. Okay, this is the linear prediction coefficient. Okay? So now the prediction error epsilon n is, okay, now we usually put, you remember we put the minus as for convenience, and then epsilon n is equal to 1 plus a1, what did I write? Yn plus a1 y n minus 1. Okay, this is the linear predictor. And in z transform, ez is equal to 1 plus a1 z to the minus 1 multiplied by y and z. So the output from the linear prediction is the prediction error. Okay? So the prediction error here is the prediction error for 1 plus a1 z to the minus 1, and this is the prediction error epsilon 1 n. Now, since the length of this linear predictor is 1, the length, okay, just as a mnemonic, so what I do, I put comma 1. So, and this is the error of a linear predictor 1. Okay, here I have already 1. And here I a1 1 c to the minus 1. Now, for the linear predictor order 2, sorry, for the predictor of length 2, okay, that means that I'm doing exactly the same. So, I have epsilon 2 n, which is equal to 1 plus a1, first the coefficient for linear predictor 2 times n z to the minus 1, plus a2 of the linear predictor 2 times z to the minus 2. This is in z transform. This is in z transform. Time y. So that means that the output here is the prediction error for the linear predictor order 2, which is the length is equal to 2 coefficient, and the coefficient are 1 plus a1 of the linear predictor order 2 times z to the minus 1 plus a of the linear predictor 2 times z to the minus 2. This is the two questions, what is written there. Okay? I simply illustrated. Now, so looking at the pole, where is the position of the pole? I mean, let me sketch it because I want to sketch the position of the pole. I'm computing by MATLAB. So roots of 1 minus 0.5 and 0.25. So the two roots of that is positioned this way. So this filter is representing two poles, and the two poles are in
0.5.
huh?
0.5.
0.20. Because it's not that this is 1/4, it's one half. And so, okay, so now is 0.25 plus minus 0.43. So the absolute value is 0.5. Okay. So now it's here and there. Okay, with the radius here and all and kind of value. And the angle is is approximately plus minus 5. No, it's a 1. Yeah, it's approximately here. So it's in radiant is approximately plus minus 1 in radiant. That's the angle. Okay. So now, so this is the position of the pole. Now, if I represent the power spectral density here, okay, the power spectral density I expect to be approximately, okay, this is pi half, so it's closer, so it's the position, the angle of the pole. Now, so I have a two resonance in corresponding of this angle, which is plus minus 1 in radian. And so the amplitude, let me see. So I don't multiply it, so it's something like that. And that's the behavior of the amplitude, the power spectral density. So here, this one is approximately SY omega, which is the power spectral density here. Now, let's go to the point. I want to find a linear predictor, the best linear predictor. Now, what does the linear predictor? The linear predictor try to put zeros to whiten, so to compensate, to decorrelate the random process which is entering here. So since let me say my weapon is only zeros, so I can only put the zeros. Now, in this case, I can only put 1 0. And due to the fact that the signals are real, the 0, if it is single, is 1. It can be positioned only here, along this axis, because I have only 1 0. So without touching, which means without making any analytics, okay? So I am going to put the 0, should be approximately here, because the 0 here, which is here, is in some way trying to compensate, to kill the two resonances which comes from the presence of the two poles. That's what I expect, okay? We will calculate analytically, but that's what I expect without touching the equation. No, and how to compute the linear predictor. The linear predictor fulfills the same equation of the Euler-Walker. Okay, so computing the linear predictor is by solving the Euler-Walker, which means knowing the autocorrelation, I want to find the coefficient of the linear predictor. So the Euler-Walker now is written in the following way. So the set of coefficients, so it's 1 plus, the set of coefficients, AI, linear predictor order n. I is going from 1 to n. Okay? The linear predictor order n is taking the autocorrelation of the input, which is Ry, in k minus I. This is equal to sigma square error, so the power of the linear prediction error, multiplied by delta I. This is the revisited Euler-Walker equation for the case of the linear prediction. So now, for this specific case, okay, so what I can do, I can calculate, for this case, I can calculate for linear predictor order 1, which means my Euler-Walker formula are, so it is A01 times R, it is K minus 0 plus A1 linear predictor 1 times R K minus 1 is equal to sigma squared epsilon delta it's I. And I is 0. So it is now in case of Euler-Walker, this coefficient is set to 1 because the polynomial is monic. And then this formula says R 0 Ry 0 plus A 1 of R Y 1. Okay. This is equal to sigma square epsilon. On the other hand, Ry1 plus A1 1 Ry0 equal 0. These are the two sets of equations. Now, so copying and solving, so that it remains to you. From Euler-Walker, okay, then I have Ry0 plus A11 Ry1 is equal to sigma square epsilon 1, which is the power of the prediction error. Ry1 plus A11 times Ry0 is equal to 0. So, solving for this, I get that A11 is equal to minus Ry1 divided by Ry0. This is the position of the first coefficient. So, in our case, by taking the values, it is minus 1.15 divide, no, Ry1 is different, is 0.23 divided by 1.50. Okay. So which is, I don't know, it's approximately minus 0.2. Okay, approximately. Okay. So that means that, you know, in this case, the zero, which is not sufficient to compensate for the two poles, you know, is not here, but it tries to be there. I mean, it's close to the circle because it's 0.2. So 0 in 0.2 is not really influencing much. Sorry, I have trouble with the cable. So, continuing. Then my linear predictor is, which is A1Z. The linear predictor is 1 plus A11Z minus 1, which is in this case is 1 minus 0.2 Z to the minus 1. Oh no, it's a 0.2, it's right. Okay. Not here. Goes. Now, computing the power of radical error. Which is by using the equation is sigma square epsilon 1 is equal to Ry0, which is equal to 1.15 plus A11, which is minus 0.2 times Ry1 and Ry1 is 0.23. Now, so look at what's happened here. Ry0, this is the power of input to linear predictor. Okay. This is 0.2 times 0.23, okay, which is 0.04. Okay, so it's minus 0.04 approximately. Now this one is the power is negative reduction due to the prediction. Now, in other words, it means the following. When I have the input, the output is trying to predict. Okay. Now, if the predictor does nothing, the power out is coincident with the power in. What is the power out coincident with the power in? It is the linear predictor order 0, which means not predicting at all. So we know from the theory that the prediction error is decreasing by the order. So that means that the power of the prediction error for 0, so the order 0, is Ry0. And the power of the prediction error when the order is 1 is Ry0 minus something. Okay? Because, you know, I can predict something of the, of the input process. Okay? Now, what's happened in this case? Do we need to compute by the unit worker? Should I start with the Euro Walker? Do I start with Euro Walker? So, should I write the following? Should I write R, Y, K plus A 1 to R, Y, K minus 1 plus A 2 to R, Y, K minus 2 equal to sigma square epsilon 2 times delta K, which is the Euler Walker?
Why don't you coincide these two since you have the transfer function?
Right. Okay. So I should not write that. Because I mean, if I want to compensate, to find the optimum pre-whitening or the optimum predictor in such a way that the error is minimum, okay? So if I cascade this filter which is all pole with this filter which is all zero, then you know this is the optimum predictor. I cannot predict more. And the output is what? Is the power of the input here. Okay? So, I mean, I don't need to write a Euler Walker. Once again. If I write a Euler Walker, then that means that this Euler Walker equation, which is the equation for the linear predictor, are the same as the Euler Walker equation, which I have to write to calculate the autocorrelation, which is 1 half R Y K minus 1 plus 1/4 R Y K minus 2 equal to delta K. This was the Euler Walker for autoregressive process order 2. And this is the Euler Walker for linear prediction. Since they are the same, there's no work to calculate, you know, the coefficient. That's another way to look at the problem. Now, so let's see if there is something interesting more to see. Now, evaluate the linear filter. Now let me make a small deviation before computing that. Okay, you will see that. I mean, now that we get practice, I mean, we would calculate quite easily. Let me introduce. I take this exercise to introduce a new concept. Okay, which we will go deeper in the future. Now. Assume that you have only Y. Assume that you don't know how to generate that. Okay, you did not. So, you know, now, that means, let me clean all. So, that means that you are now in a position where you know, for instance, that Y is obtained by an autoregressive order process. Okay, but you don't know the order. So, you are here. So you take a set of values, and you want to calculate the filter which create these autoregressive process. Okay, so that's what we want to do. So now what we can do is this: we can write here a linear predictor. So we make a linear prediction. Now, what we can do, we can play with a linear prediction, for instance, by increasing the order, okay, until the output is white. So, if the output is white, the linear predictor is perfectly calculating what? Not the filter, but the power spectral density here. Because remember, if I have a linear predictor which perfectly compensates for that, I get a white random process as output. So if I manipulate the linear predictor, manipulate means computing. Huh? I'm not saying manipulate in a strange way. It's computing. So, which means how to compute a linear predictor. You know, I'm using Euler-Walker. So we remember that, you know, the Euler-Walker equation puts together in relationship either the autocorrelation K with the coefficient A, K, M, okay? Which is the coefficient of the linear prediction. So how do I make it? I take it, I compute the autocorrelation coefficient here. Now I can compute the autocorrelation coefficient by a sample estimate. So what I do, you know, I calculate by autocor or cross-core function by MATLAB, right? You know the cross correlation, okay? When you don't know what to say, when you get the first time a signal, you try to understand what is the property, and so don't you calculate the correlation of the signal. You want to see if, for instance, a signal has some periodic structure. You want to see, you know, what is the power spectral density. And so, I mean, that is a basic you do. Okay, so you did autonomously, I mean, when we did the last workshop, some of you started to calculate the correlation. Okay, so that is a right approach, that is a correct approach. So when you're here, you know, what you calculate, you get the estimate of RYK. Okay? These are the estimates. So you calculate RYK as a sample estimate. So when you implement it by cross-core or autocore in MATLAB, autocore and cross-core, you know, takes a block of n samples. Imagine a block of n samples. And then, you know, using this block of n samples from Y, then what you do is MATLAB makes the following. So calculate Y n, Y n minus k. And then is a summing for n, all the n that I have. Okay? So, for, you know, since the index is here, this is what MATLAB computes. And this is the sample estimate. So this is the best estimate that you can calculate having the data. Okay? So this is, I don't know, is it GS core? Cross core?
X core.
X core. Which is the cross correlation we did separate, right? Okay. So you compute this way, that's what you get. Then, you know, what you do, you take this and you put into there. Okay? And then, you know, in place of the autocorrelation, you put the sample estimate of the autocorrelation. And then, from this, you get the prediction filter. Now, you know, what you can do is that you start with the linear predictor of a certain order. So you start with the prediction error 0, which means do nothing. Then you start with the linear prediction error 1. Then you start with linear prediction error 2. When you start with linear prediction error 3, then you start with the linear prediction error 4, 5, 6, 1. Then also 1, 2, 3, 4, 5. This is the order. Okay? So what we discovered here? We discovered that linear predictor order 3 is enough to pre-widen the data. In theory, which means in a more abstract way, this plot is going constant. Okay? But you know, since you are sample estimating the parameter, you have a kind of need. Okay? Kind of need, kind of discontinuity. So we know that this is a linear. The linear predictor order 3 is at the best completely decorrelating the sample, the prediction error out. So that means that specific, imagine here, that specific linear predictor Okay, so we have a certain filter A3, 3 is the order, which is obtaining here epsilon 3, okay, which is approximately wide. Okay, it's operative, it's practical, it's not fantastic. Okay, so this is what I do. But now, if this one is wide, that means that this filter is completely compensating this filter. Now imagine that ideally, I don't know how was the filter because I give you the data. Imagine it's like in a wash, in a homework. I give you the data and then I ask you, what is the power spectral density? What is the property of this random process? Now you might start calculating the autocorrelation. When you calculate the autocorrelation, you know, you have a lot of samples. Huh? Now, you know, if you do this way, you can obtain this polynomial, which is now in the order of 3, 4, whatever. Okay? That means these linear predictors almost, close to perfectly compensate the correlation property of the input signal. If this filter has the property of decorrelating the input signal, that means that this, you know, the polynomial which correlated the data is 1 over A3. So we essentially found indirectly by an inverse method, we found that this unknown filter was 1 over A3Z. Let's try it again. You have a record. So that's the point, you know. So that means that in case you have a random process, by calculating the sample estimate, which is this, okay, score, okay, by calculating the sample estimate using the Euler Walker and searching by solving for the Euler Walker until I get this knee. This knee is given in the order, okay? I can get the best linear predictor, which has the property of completely or at most completely decorrelating the error here. If this guy is completely decorrelating the error, this means that I have also an uncorrelated random process which is entering here, which is filtered there, is correlated according to the filter, and then I generate another filter which is decorrelating. So the chain is white, uncorrelated, filtering, correlated, filtering, decorrelated. So that means that this filter is the inverse of that.
This approach is to what extent reliable with the presence of the noise?
Where is the noise?
Right there. I mean, no. Addition noise to the Y.
No. Is, you know, I mean, without the noise is exact. With the noise is approximate.
It's still working to...
It's always work because, I mean, alpha is not a deterministic signal. It's a random process. So we are all dealing with a random process. So don't confuse that, you know, the RY that I'm computing is a deterministic one, is random. And so it's a sample estimate for the process Y, which is random due to the fact that alpha is random.
So the error at epsilon 3 is a sample error. Sample means that is already estimated because...
Yeah, but that error, you know, is, I mean, at the best is white. So if epsilon 3 is white, it means that it contains no correlation. If epsilon 3 is white, it means that there is nothing else that I can use in epsilon 3 to predict the signal, to predict the signal itself. So once I completely decorrelate it, there is nothing else that I can predict on the signal, because remember, the linear prediction is predicting on the signal using itself. So that means that, you know, a white process, we said, you know, a few weeks ago when we started, a white process is a process where the samples cannot predict any others except itself. So we are, going to the degenerate case that epsilon 3 cannot predict anything. And so, since epsilon 3 cannot predict anything, which means it's white, then we reach the position where epsilon 3 coincides with alpha. Remember, I don't know alpha. In all these problems, I don't know alpha. Now, everything I am discussing now, which I'm simply anticipating a little bit, is called spectral analysis. So spectral analysis is to estimate the correlation properties of Y by using this clever method, which is by whitening or by linear prediction of the specific random problem. Now I told you, the last exercise, I wanted to anticipate this. The last exercise, which is very easy. So it says, I want to estimate alpha from X. Okay? So let me leave you these exercise, a solution for the exercise, which is very quick. So, this is the filter, which is AH, okay? So HZ, the filter HZ by Wiener. Now you can solve, when you go home, you can check it, okay? And this one is okay. So the denominator is RXXZ, which already we computed, which is at the end, and here I have a AZX star. X star contains beta, and so then when I need to correlate this with that, in the numerator I have 1 minus z to the minus 1, and it is 1 minus 1 half z to the minus 1 plus 1/4 z to the minus 2. Okay, this is just to leave you the solution for this exercise for the video. Then you can check yourself. Now, as I told you, you are always well skilled with Wiener, and usually once you made a couple, 2, 3 exercises, they are very easy to compute. Do yourself the last. So, the remaining part, differently from C1, 2. Here we use a set of samples. Look at similar to the previous one, to estimate y, blah, blah, blah. Now, we did, is similar to the previous exercise. Now, the MSC estimator in D1, this one, can be implemented in adaptive form by LMS adaptive estimation method. Define the LMS update form, which means the formula. Evaluate the minimum number of steps for LMS algorithm to reach the conversion in mean, which is the ratio between lambda max and lambda mean of which matrix, since it is D1 of the matrix X. X is those processes at the end. Okay? Evaluate the loss, if any, in the number of steps to reach the convergence of the mean square error. So this means that making the convergence of the mean square error, the mu steps is smaller. Since it's smaller, the convergence is slower. Okay? So it might be possible that in this case, since the power spectral density here, I have a 0 in 0. Okay? So the power spectral density of this guy here is approximately, okay? So I have a 2 resonance, 1 0, 1 resonance, and then a 6. So the fact that I put 1 0 here, this is 0, okay, makes the dispersion, so the ratio between lambda max and lambda mean, to be very big. Okay? So I put intentionally that to 0. And so that means that in this case, the convergence is pretty slow. So I accelerated because I want to give you these results. Okay. That's it.